Hello, everyone. My name is Diana Croniale, and in BTS, I'm the educational manager. During this webinar, we are talking about how to evaluate walking from a dynamic point of view, going to focus our attention on the importance and the role that the forces play to perform this type of movement. I would like to start by recalling a theoretical concept based on the laws of physics, and that we have surely studied at school. For every action, there is an equal and opposite reaction. So every time our feet come into contact with the ground, an exchange of forces is established with it. We load a force on the ground, which is the sum of our body weight and all the forces developed by the muscle tendon tissues, and the ground replies with a force of equal intensity, but in the opposite direction, directed against us. During the stance phase of the gait cycle, as long as the foot remains into contact with the ground, the subject is loading a force on the ground. Time by time, during the three different foot rolling phases, this force changes its intensity and its direction. As I already said, in response, the ground develops a force of the same intensity, but in the opposite direction against the subject. This force is called GRF, ground reaction force, and now we are going to analyze it. The ground reaction force is represented by a three-dimensional vector directed in the space, and it can be divided into three different components. Two components lie on the horizontal plane, and the third component is perpendicular to this plane. The two forces lying on the plane are the anterior-posterior component and the medial-lateral component. The force perpendicular to the plane represents the vertical component. In this graph, the pattern of the anterior-posterior force during the walk is shown. I would like to point out immediately that on the horizontal axis, you don't find the entire gait cycle as you are usual to visualize, but the 100% is the only stance phase. On the vertical axis, the force value is expressed in terms of percentage in respect with the body weight, and not in Newton as a measured unit. This normalization obviously allows to compare the force among different subjects. As you can see, this force is characterized by a first negative peak and a second positive peak. Taking into account that the force is directly related to the acceleration which the center of body mass is subjected to, since we know that force is equal to mass per acceleration, we can say that when the foot comes into contact with the ground to start the gait cycle, and during all the first rolling of the foot around the heel, the center of mass undergoes a deceleration along the anterior-posterior direction. When the graph crosses the zero line, the zero axis, it means that this component is zero, and all that happens during the single support phase. When the limb is in the posterior position during the second phase of the stance, the curve becomes positive, and the peak is representative of the acceleration which the center of mass is subjected to in order to allow its forward movement along the walking direction. Here we find the medial lateral component. Usually this force is very small, and for all the duration of the stance phase, it is directed medially. Excluding the first and the last part of the curve related to the double support phases, we can say that during the single support phase on one single limb, the ground reaction force generates an acceleration of the center of mass towards the contralateral limb in the medial direction. Finally, we have the vertical component, which, as you can see here, is characterized by a double peak. To correctly assess this force, it's useful to keep in mind the body weight line, which is obviously fixed on 100% of the vertical axis. When the force exceeds the line of the body weight, the center of body mass is accelerating, and this happens during the loading response, and during the terminal phase of the propulsion. However, when the force is below the body weight line, the center of mass is decelerating, and this happens during the central phase of the single support. Okay, till now we have analyzed the three force components of the ground reaction force, but it's also useful to understand how it's possible to measure these forces. Obviously, the force measuring instrument is the force platform, and the BTS provides P6000 force plate, which is a totally digital triaxial dynamometric platform, able to measure the ground reaction forces generated by the subject standing or moving across it, allowing a complete analysis of the static or dynamic postural condition. The P6000 platform is the single module, but it was born to create a real modular sensory floor. Unlike other platforms on the market in which the connecting cable is on one of the four sides, in BTS P6000 platform, the cable has been moved from the lateral side to the lower part of the platform, keeping all four lateral sides completely free. In this way, the modules can be placed perfectly one adjacent to the others, along all four sides at the same time, without space among them, so that finally it's possible to create, as I said, a real sensoride floor, any size large, on which the patient can move freely. Moreover, as I already said, because the modules are completely digital, also the foot contacts that occur across two adjacent modules generate an unique correct force data without discontinuity. As you can see here in the example, starting from two force contributions measured by two different modules, a single resulting force is created exactly as if the contact of the foot had occurred at the center of a single module. Thanks to the characteristics of the P6000 platform just described, within the gait analysis laboratory, BTS suggests to use 6 or 8 modules in order to create two different rows of platform. One dedicated to recording the contacts of the right foot, and the other row dedicated to the registration of the left foot contacts. In this way, it's immediate to understand how the acquisition of the force data becomes easy and fast for all walking trials, regardless of the patient's limitation, especially in terms of reduced stride length, shorter stride length. Even for the patient, the exam is not tiring and demanding, thanks to the important time saving. Therefore, we have seen so far that the force platforms allow to evaluate the walk from the dynamic point of view. But we know that for a complete gait analysis in the motion analysis laboratory, the force platforms are always integrated into the optoelectronic system with infrared light cameras for the evaluation of kinematics, that is, as you know, spatial temporal parameters and joint angles. As you know, thanks to the acquisition of the reflective markers placed on the patient in precise anatomical landmarks, it's possible to obtain the joint center of rotation. By merging together the joint centers of rotation obtained from the kinematic system and the forces measured by the platforms, we can have information about the joint moments and the joint powers. Before going into the explanation of the joint moments during walking, I think it's useful to recall some theoretical concepts. The moment or torque that allows an object to rotate arises when a force is applied to a hinged body that is fixed and can rotate around a fulcrum. The distance of the fulcrum from the force application line is the lever arm. The product of the force per lever arm is the moment. This theory is the same one that is also at the base of the joint moment concept, where the applied force is the ground reaction force, and the fulcrum is every single joint center of rotation. Therefore, time by time, during the whole foot progression on the ground reaction force generates a joint moment at each joint level. Let's consider this precise moment of the stance phase, exactly the foot initial contact with the ground. First of all, it's important to assess if the application line of the ground reaction force is forward or backward with respect to the joint center of rotation. Compared to the center of rotation of the ankle, for example, the ground reaction force is backward, and so it is generating an external plantar flexor moment. According to the third principle of dynamics, that is the Newton's third law or principle of action and reaction, this external moment is contrasted by an internal dorsiflexor moment generated by our body as response. If this internal reaction of our body was not present, when the foot contact with the ground occurs, the foot would fall down because it was subjected to the external plantar flexor moment. Similarly, also the knee would perform a flexion movement, moving the joint center down because it was subjected to an external flexion moment. But all that doesn't happen because an extensor moment, internal extensor moment, is opposing from the inside. Finally, at the hip level, the external moment is a flexor moment, and therefore the internal moment is an extensor moment. It's important to underline that the moments that are reported on the gait analysis report are internal moments, because from the clinical point of view, it's useful to understand with which muscles the patient is working. Obviously, if at the ankle level, we say that the internal moment is a dorsiflexor moment, it means that dorsiflexor muscles are working to generate this response. At the knee and hip level, the extensor muscles are working in this precise moment of the gait cycle. Now, let's explain the concept of joint power. First of all, it's essential to remember which are the two different ways to define the muscle's work. Starting from the resting position, the muscle fibers can generate force through a contraction that makes the fiber shorter. In this case, we talk about concentric muscle work, and the power is generated. On the contrary, muscle fibers can also generate force through a stretching process. In this case, we talk about eccentric muscle work, and the power is absorbed. Therefore, from the evaluation of joint power, it's possible to deduce how the muscles are working. In this slide, I would like to summarize the two fundamental concepts just explained. From the evaluation of the joint moment, we can understand which muscles are working. On the other hand, from the analysis of the joint power, we can deduce how the muscles are working. Here we find the graphs of the moment and of the powers of hip, knee, and ankle during the gait cycle. Let's try now to read together the graphs of moment and power related to the ankle joint. At the foot initial contact on the ground and during the loading response, during which we have the first foot rocker around the heel, the ground reaction force is behind the center of rotation of the ankle. And so it's generating an external plantar flexor moment. For this reason, as you can see here in the graph, we find a dorsiflexor moment has response, because in this phase, the dorsiflexor muscles are working. At the same time, if we give a look at the power in the same phase, of course, we can see that the power is absorbed. And this is exactly what we expected, because, as you know, in this phase, the dorsiflexor muscles are working in eccentric mode because they are lengthening to control the fall of the foot. For example, let's think to the tibialis anterior muscle. Now, when the ground reaction force passes exactly through the joint center, the moment is zero because the lever arm is null. During the single support phase, when the force begins to move and pass anteriorly to the ankle rotation center, the internal moment becomes plantar flexor. All that means that the plantar flexor muscles are working in eccentric mode with an absorption of power. Let's remember that in this phase, the plantar flexor muscles, for example, the sura triceps, are lengthening to generate force and control the progression of the tibia on the foot. Finally, when the limb has moved to the posterior position and the last foot rocker around the metatarsal heads and fingers is happening, the internal moment is still a plantar flexor. But now there is a generation of power, because, as we know, the plantar flexor muscles are working in concentric mode to generate the necessary propulsive force that will push the limb forward and start the swing phase. Now, let's see what happens at the knee level. Then I will let you evaluate the hip joint by yourself. Okay, so at the moment of the foot initial contact on the ground and during the loading response, the ground reaction force is backward with respect to the knee center of rotation. Therefore, the external moment is a flexor moment. The internal moment is extensor. In this phase, the extensor muscles, the quadriceps, of course, are working in eccentric mode with power absorption to control the knee flexion. In the single support phase, the force is still slightly behind the knee center. So the internal moment is still extensor, but the moment is decreasing because the lever arm is reducing a lot. But the power is now generated because the extensor muscles are working in concentric way to extend the knee. When the ground reaction force passes in front of the knee center of rotation, the internal moment becomes flexor. with a very small power absorption. Why we have power absorption? Let's remember that a few minutes ago, I have just said that the plantar flexor muscles are working in eccentric way on the ankle. The plantar flexor muscles, such as medial and lateral gastrocnemius, are biarticular muscles. And in this phase, they also have an action on the knee. Finally, we find again a second peak of extensor moment. The extensor muscles are now working in eccentric way with power absorption to control the knee flexion that is caused by the pushing force of the ankle plantar flexor muscles. Okay, well, the webinar is over. Thank you very much for your attention. I hope that the concepts discussed have been clear and can be useful in your work practice. Thanks again, and I would like to wish everyone Merry Christmas. See you next year. Bye-bye.